This video is on fusion and stars. Question 1. Define nuclear fusion. Nuclear fusion is when two or more atomic nuclei collide at very high energy and fuse together into a new nucleus. The binding energy per nucleon of the new nucleus is more stable than the original two nuclei. Temperatures of greater than 10,000 Kelvin is required. So you could see fusion happens to all of these elements to the left of this vertical line. They all want to get closer to iron. And fission happens to all of the elements to the right of this vertical line. In fission, these elements want to break down and become closer to iron. Question 2. Give 2 examples of nuclear fusion. From this website, I was able to get these 2 examples here in red. Hydrogen plus hydrogen becomes helium plus a neutron plus energy. And you see, this is not hydrogen, this is deuterium plus tritium. Also, hydrogen plus helium becomes helium plus hydrogen plus energy. But this is helium with 1 neutron. It ends up becoming helium with 2 neutrons. Question 3. Define celestial. Celestial means relating to the sky. Question 4. Define star. It's a celestial body that generates light and other radiant energy and consists of a mass of gas held together by its own gravity, in which the energy generated by nuclear reactions in the interior is balanced by the outflow of energy to the surface. The inward directed gravitational forces are balanced by the outward directed gas and radiation pressures. So the sun is a star. Question 5. Define thermal gas pressure. The outwards pressure created by the contraction of the mass in the star. Question 6. Define radiation pressure. That's the outwards pressure created by emitted radiation of the star. Question 7. Define gravitational pressure. That's the inwards pressure of a star. Question 8. Define stellar equilibrium. Remember, in an earlier worksheet, equilibrium means sigma F is 0, A is 0, V is constant. We have static and dynamic equilibrium. Now we're talking about stellar equilibrium. So when the thermal gas pressure and radiation pressure is equal to the gravitational pressure, the star remains the same size, is stable and unchanging. You see, force of gravity balances the thermal force. Tussle between gravity and thermal pressure. Question 5. Define main sequence star. When a star is in stellar equilibrium, these stars fuse hydrogen atoms to form helium atoms. About 90% of the stars in the universe are main sequence stars. These are the most numerous true stars of the universe. Question 10. Define sun. That's our closest star. Question 12. Describe the proton-proton cycle. So this is a 3-step cycle for fusion in a star. So take a look at step 1, 2, and 3. So this is an image of the proton-proton cycle. Question 12. Define apparent brightness B. What are its units? The intensity I equals power per unit area received perpendicular to the direction of propagation at the Earth. Apparent brightness B has units of watts over meters squared. Question 13. Define luminosity. L units. The total power a star radiates in the form of electromagnetic waves. Luminosity has units of watts, which is the same as power. Question 14, define a perfect black body. It's a perfect absorber of energy, emits maximum possible radiation, does not have to appear black. All stars like the sun are considered to be black bodies. Has an emissivity of 1 and an albedo of 0. If you forgot what emissivity and albedo is, take a look at a previous worksheet. Question 15, describe Wien's displacement law. Recall this from an earlier video. Lambda max T equals 2.9 times 10 to the minus 3 meters Kelvin. Why are the units meters Kelvin on the right side? Because the units are meters Kelvin on the left side. Okay. As the temperature of a black body increases, then the maximum wavelength emitted decreases. So do memorize this graph. You see the maximum wavelength emitted, its wavelength decreases. Question 7, describe the absorption spectrum. Okay, so recall this from an earlier video. We can use absorption spectrum to determine which elements a star is made of. Energy goes through a sample of gas. A specific amount of energy will be absorbed by electrons in the atom, and then the electron will go to a higher energy level. The electron will then return to its lower energy level. To conserve energy, the lost energy will be emitted as a photon in a random direction. The vertical black bars in an absorption spectrum image the specific energy or wavelengths absorbed by the sample. So recall these equations, E equals HF and V equals lambda F. So these are the fingerprints of an element. Question 17, describe main sequence stars. These are the most common stars. They fuse hydrogen to helium. About 90% of the known stars are main sequence stars. The sun is a main sequence star. Question 18, describe the Hertzsprung-Russell diagram. A diagram which characterizes the stars by luminosity and temperature. Temperature increases to the left. Both the luminosity and temperature axes are usually logarithmic. So take a look at this. Look at the temperature. We got like 25,000 Kelvin, and then as you go to the right, the temperature decreases. And take a look at the luminosity. You see, this is exponential, like exponents, okay? So remember this. Both the luminosity and temperature axis are usually logarithmic. So whatever graph you're given in a book or on a test, make sure you take a look at the units and make sure you see which direction is positive. And we have a class of stars here. That's the meaning of O, B, A, F, G, K, M. So we got main sequence stars here, which follow this curve. And then we got giants here, and we got supergiants. We could find out the luminosity and temperature of these stars. And we got some white dwarfs here on the bottom left. Describe the instability strip. Stars listed in the Hertzsprung-Russell diagram which are not in stellar equilibrium. The outward thermal gas pressure and outward radiation gas pressure is not equal to the inward gravitational pressure. These stars are increasing and decreasing their volume. So the instability strip are stars which are not stable. Define a red giant, a red supergiant, and a dwarf star. So we could see here, we got supergiants, we got giants, and we got these white dwarfs. So these giants are like red giants and red supergiants and white dwarfs here. So a red supergiant is a very large red giant. A dwarf star is a star which the core of the giant red star, which remains after planetary nebulae, means after it dies down, the energy gets expended. And this is a red giant, a very large, cool reddish star with great luminosity. Most stars become red giants or red supergiants at the end of their time on the main sequence. They have expanded considerably from their original volume. Question 23. Define electron degeneracy pressure. Electrons act like a gas to prevent a star from collapsing further so it can remain stable for a long time. Question 24. Define a white dwarf. It's the end result of the explosion of a red giant. This is after electron degeneracy pressure. It is a small and dense star in which no nuclear reactions take place. It is very hot, but its small size gives low luminosity. So we go from a main sequence star to a red giant star to a white dwarf. And after a supernova, the red supergiant becomes a neutron star or black hole. Question 26. Describe the term evolutionary path. So it's a luminosity versus temperature graph which shows a main sequence star expanding to a red giant and changing over time. So you could see the main sequence star in yellow, this strip. Look at this black part here. First, it becomes a main sequence star. Its luminosity increases, its temperature is pretty much the same. Then it decreases its temperature. Then the luminosity stays kind of constant. The temperature increases. Then the luminosity decreases as the temperature increases, then decreases, and the star becomes a white dwarf. Now take a look at this large star, because on the bottom right it says small star or large star. The large star decreases its temperature, increases its luminosity. Describe the equation L is proportional to m to the 3.5. For a main sequence star, its luminosity is proportional to 3.5 times its mass. It's an approximate and generalized equation. Question 25. Define astronomical unit. The mean distance between the Earth and the Sun. So one astronomical unit is 1.5 times 10 to the 11 meters. Question 25. Define light year. The total distance an electromagnetic wave like light travels in a vacuum in 1 year. Question 30. Define stellar parallax. This is determining the distance from stars by observing their motion compared to a stationary star which is further away in the background. Question 31. Define parallax angle. So memorize this image. The parallax angle is the angle between the Earth at one time of year and the Earth 6 months later. So it's going to be this angle here. Look at star A. There's like an acute angle. Question 32. Define arc second. 1 degree is 3,600 arc seconds. Question 33. Define parsec. It's a distance to a star that has a parallax angle of 1 arc second. Question 34. Describe the equation d parsec equals 1 over p arc second. P arc second is a parallax angle measured in arc seconds. Remember, 1 degree is 3,600 arc seconds. D parsecs is the distance measured in parsecs. Remember that a parsec is a distance to a star that has a parallax angle of 1 arc second. So 1 parsec is equal to 3.26 light years. So So that's distance. Question 35. An example of a fusion reaction is when deuterium and tritium combine to create helium, a neutron, and energy. Determine the energy released from this reaction with a given data and the change in mass from this reaction. So you could see what I did in part A, yeah? Okay. And you could see what I did in part B. Question 36. The temperature of a main sequence star is approximately 2.5 times 10 to the 4 K. Part A. Determine the peak wavelength of this main sequence star. We're going to use Wien's displacement law and solve for lambda max. Part B. Determine an approximate value of the luminosity of this main sequence star. We have to take a look at the Hertzsprung-Russell diagram. So we're given 25,000 Kelvin in the problem. So it's 25,000 Kelvin here. We go down and then we go to the right. Because this 25,000, when we go down, it touches this strip for main sequence. So we go to the right and it's about this value here, between 10 to the 2 and 10 to the 4. So the luminosity is about this, 3.42 times 10 to the 30 watts. Okay. Part C, determine an approximate value for its radius. You're going to remember this from an earlier video. Luminosity is sigma A t to the 4. A is the surface area of the sphere, 4 pi r squared. Let's solve for r squared, then take the square root. Question 37. The surface temperature of a main sequence star is approximately 1 times 10 to the 4 K. Part A, use a Hertzsprung-Russell diagram to estimate the luminosity of the star. So once again, we're going to go to 10,000 K on the graph. And then we're going to go down. Once we hit this main sequence strip, we're going to go to the right, and that's the luminosity. Okay? It's about 10 to the 2, which is like close to 100. So that's where we get this 90. Okay? Just like in this previous problem, this is about 9,000 on the vertical intercept. So that's where we get 9,000 here. Part B, the apparent brightness of this main sequence star is approximately 1.6 times 10 to the minus 9 watts over meter squared. Determine the approximate distance between this main sequence star and Earth. We're going to use this equation from a previous worksheet. And we're just going to solve for D. Question 20. The parallax angle to a star is 0.320 arc seconds. Determine the distance in meters to the star. So we're going to convert parsec to meters. Finally, the parallax angle for Betelgeuse is approximately 5.95 times 10 to the 3 arc seconds. Determine the distance of Betelgeuse from Earth in parsecs, meters, light years, and astronomical units. So this is how we solve part A in parsecs. Part B in meters, I'm just converting. Part C in light years, once again I'm converting. Finally, part D in astronomical units.